So why do most 3D pipelines fail and how to fix them? So I created this with a system kind of view that works in 12 steps, and I will bring you on this journey to give you all the necessary tools and solutions to fix that. For the new folks here, I'm Florent, the author of 3D Data Science with Python book, published with O'Reilly, and head consultant for Fortune 500. Also founder of the 3D Geodata Academy, I help professionals build operational systems. So the first main issue here is what I call the fragmentation problem. Most companies I've worked with have at least 5 to 10 different tools that will each target a specific workflow or problem. So my question here is, why do having so many specialized tools actually slow down the process instead of speeding it up? If I can give you an example, with this company, they had 3D data acquisition with terrestrial laser scanner, with software Cyclone, and then after they were using Reality Scan now for anything photogrammetry related, and then they were moving into AutoCAD and then Revit for the BIM modeling. So while this is super useful to answer specific clients' requests, complexify a lot the chain, but the tools here is not the problem. So what is it? And that's what I will also target on. The second issue is the manual handoff. So every tool requires human intervention, and this can be a big bottleneck. What happens when someone has to click import, then export to go out of the software? It means that you have a lot of dead ends here. And I've seen a project where one person is just on vacation and the full pipeline cannot advance. You have a 40K project on the line and you cannot move it forward because you are missing this specific person that knows exactly what to do in this kind of software, import, export, and you cannot move without that. So the natural question is, if the manual handoff is the bottleneck, what is the solution? And that's where we see the issue number 3, which I will call the automation illusion. Many teams will try to automate tools by scripting lines in between tools to make the interaction works. This is a great idea, but why do most of this project fails within the next 3 months? Well, let me share an example. I had this team that was writing a call map script that were handling a lot of pictures, and then it was pushing out all that as an output from a call map to Blender that was expecting the exact format. So when there was an update with call map and the structuration behind that, the entire workflow just stopped working. And in between, the person moved to another company. And of course, the team that I was managing at the time was stuck. So the script broke, team went back to manual, and we were stuck. So now, if automation is fragile, what is the solution? And that's where I want to make sure that we establish a very clear architecture that knows exactly what changed, what has to be changed, and what stay as it is. So that will push our thinking, our design system into a 3-tier architecture layers. So what if we designed this architecture like software engineers do, software actually. And that's what I'm doing here. And we have 3 main components in this architecture that you can see, 5, 6, and 7. This will be the ingest block. This will be the processing block, and this will be the deploy block. And the idea is to make sure that we avoid this struggle, the fragmentation, the manual handoff, and the automation that breaks. So here you handle all the data that comes in. It can be images, it can be text, it can be a point cloud, it can be meshes. Okay, sorry about that. It can be Gaussian splitting, any input that needs to be processed. It's all handled here with the file format. And the trick is, why should the rest of the pipeline worry about which format you have? So in this ingest block, traditionally, this was EDL workflow that we had, but here it evolved a bit. That's why I had this nice ingesting word. What we want to make sure is what is out of that is something that will stand the test of time. And you remember from other videos, if you want to have something that stands 10 years or plus, you go with ASCII file format. If you want something that is more efficient, you go with binary file format. So here, Python is here for the long haul. So we can say, all right, so why not export everything as an NumPy array that we structure as an object that is very handy? And that means that all the rest will work with that. So of course, we need to be mindful about the software stack that we have, if it's proprietary, if not. But nevertheless, the idea is all that is linked with the data is handled here. So now the question remains, with clean output, what does this processing layer actually do? And the starting point is pure algorithm that works on standardized data. That's what we want. And that's already a very nice trick here. Standardized data, pure algorithm. All right, so here, what is complicated is actually to make sure that you work in a modular fashion, so that if you have any time to switch between using Rensack over dbScan or over k-means, over a CNN, over a transformer architecture, that you can do so without headaches. And it's just a matter of switching a function, switching a class if you are coding, or switching a specific modules from a specific software API. So in a way, it's like playing with Lego blocks. And when I set up such a system early on in my PhD, it was really easy at the time because I had already this architecture kind of design thinking kind of way, and I could switch at the time using Rensack for region growing for plane detection, and then move my rule-based semantic segmentation with 3D geometric deep learning without any headache. And I had handled all the input outputs kind of things, and in the process layer as well. It was very clear, like Lego bricks, what stands below and what will be built above. Everything was fitting. So this is great. Now we have clean data and flexible processing. But how do we handle deliverables to our clients? And this is where comes my deploy layer philosophy, because different clients need different deliverables, and we need to be able to cope with that. So how do you avoid to rebuild the entire pipeline every time your client asks a little modification? I can share some ways that I saw was a huge bottleneck. For example, when you do photogrammetric project, you gather a lot of images, right? And if you're tied down to a specific software with a specific file format that you cannot go out of, and you didn't work on the standardized input and output, 6 months down the line, your client says, oh, wait, there is an issue because I see a double skin there. Can you rework it? So if you didn't had a system to cope with that, then you would either go redo everything from scratch, or reuse the next existing project, but then you have to retrieve that, or anything else. But it's very cumbersome, and here, with the deploy strategy, we need to make sure that this kind of thing does not happen. So, for example, here, if your clients want a LAS file, a point cloud, this is fine. But then, after that, you want CTGML, this is fine. If you want a Pottery web viewer, this is also fine. This is all in the deploy, but it works outside of the various process and ingestion layers. So this is fine in theory, right? But what about when things break? And that's where I also want to give you some pointers. And here it's the first thing is the observability requirement. So this little thing here means that you will want to log as much as possible. So the deploy will have a nice GUI, right? You will have a point cloud, you will have a floor plan. So all these kind of things will need also to be logged. And this is very important because you see why failure happen and where they actually happen, so that it's much more important than preventing all failure. I can think of this one time where I had this client that complained that my team delivered a point cloud with wrong colors. Because we had this logging system in place, we knew exactly that it was at a specific stage in the process layer that we had to change through the logs. We didn't have to retro-engineer anything. We could just look at that without having the specialized engineer working on specific tasks. So all of this is also super handy whenever you want to scale. And with scale come usually more people or AI involved. So it's very important to log, report, and validate any step. So now we have the architecture, but how do we implement it strategically? And that will talk on my last 3 main points here. And the first thing is configuration over code principle. So it's very important not to rewrite the code of your pipeline, but just to write the configuration when you need to make a change to the pipeline. So for example, this is something I do very often. And if you used PDAL in the past with Python, it works kind of in a similar fashion, but using external ASCII like JSON structured files will help you decide what's happening in your workflow. This could be also abstracted. It doesn't need to be a JSON file. That could be an AI chat with who you interact, and it will down the line work on that. But essentially, you want to make sure that your pipeline is orchestrated by one or maybe a couple of clear pipeline orchestration solutions. So this helps immensely. Now, what happens when you collaborate or where something goes big? And this is where I want to speak about the next stage. The single source of truth. We have intermediate results, and they all should live in the same place. with version control. And here you see my little drawing. What is that? Is something that we'll call a data lake, but essentially this is for you to have this specific term for you to search, because this is very handy and it should inspire you about knowing exactly who, when, or what accesses some specific aspect of the process, the data, or anything that goes into the pipeline. This should all be there. Why? Because this will avoid you discussion like, oh, I thought I did process that. With that, you have every process file to a structured storage infrastructure. So it's very easy to go and check out the metadata to know exactly this kind of answers. So we have covered the complete system. So this solves today's problem, but what about scaling? And this is something very important. Usually what I recommend is to have a horizontal scaling strategy. This means that good scaling means you can add a computer, not rewrite the entire code. Just build gradually. Start with one computer, and then you extend to 5 computers, and then you extend to specific clusters, and then you extend to various Docker systems. So this is up to you, but it should be scalable or designed in a way that allows you to work onto this ingest process and deploy the 3-tier level architecture layers. All right, so now to debunk something, I have some common mistakes that I saw and I want to share with you. The first one is mixing concept. Putting export logic in processing code. This is something that you should avoid if you can. The second thing is no validation, assuming everything or the data is always perfect. It's never perfect and never will be. So it's very important to have this kind of validation. And the last thing is too tight coupling. If you have a chain of processes, if the first one fails, the entire pipeline fails. So it's very important to have something where all these 3 mistakes are avoided, because that's the thing that will cost you more on the get-go. I hope all this experience shared and the vision about how you move around that will help you in your venture. If you want to know more, I will encourage you to check out the 3D GeoAI sprint that I created. It gives you my full strategic roadmap to create innovation from ideas, and also give you directly a solution GeoAI for 3D point cloud data with code and everything. So if that sounds good to you, just go down below and let's see each other in another video. Bye-bye.